Lesson 6, Part 3. The procedure of the wet process are basically the same with the dry processes, which can be divided into 3 stages: raw material preparation, clinker calcination, and cement grinding. All of these stages are covered earlier and we mentioned before. Similar to the dry process, materials also need to undergo carrying, primary crushing, secondary crushing, proportioning, and grinding in the raw materials preparation stage of the wet process. The biggest difference between the two methods is that in the wet process, water is usually required as a process media added in the raw mix to form slurry. After mixing and blending, the slurry will be stored in the slurry tank waiting for future processing, while in the dry method, cement production line, the raw mix doesn't need water. In the calcinated stage, the cement kiln used by the wet process is longer in comparison to the dry processes, and there is no preheater and precalciner. In front of the kiln. This is a rotary kiln. Burning zone to rotary kiln. The temperature is in a cement kiln can reach 1400 1500 degrees Celsius. Slurry in it's heated and dried, and finally forming the clinker compounds, namely D-calcium silicate, 3-calcium silicate. Tricalcium aluminate and tetracalcium aluminoferrite. Clinker is a kind of particle with a variety of size and dark green color. After cooled down, in the great cooler, they will be sent into the grinding mill for the last processing. In the last stage, clinker will be ground into qualified fines in grinding mills. During the processes, we usually add some gypsum and other materials into clinker to give the final cement product different properties and usages. For example, we add gypsum to obtain the ordinary Portland cement and add gypsum and fly ash to obtain the Pozzolana Portland cement. Aggregates. These are materials that are mixed with the cement to form concrete. They are classified as fine or coarse aggregate. Fine aggregates are those that will pass a standard 5 mm sieve, while coarse aggregates are retained on a standard 5 mm sieve. This is a 5 aggregate and this is a coarse aggregate. Aggregates form the bulk of a concrete mix and comprise graded sand and gravel. Sometimes sand is termed as a fine aggregate and the gravel fraction as coarse aggregates. These materials are combined with cement powder and with cement powder and water and forms the basis of a concrete mix. Also, inert aggregates form a large fraction of a concrete mix and are important. Aggregate may be formed from mined gravel or gravel reclaimed from the sea and subsequently washed. Both of these aggregate types need to be carefully managed to ensure the distribution of particles is correct for concrete manufacture. This is particularly so of marine aggregates which tend to contain larger proportion of single-sized particles. Alternatively, rocks may be crushed to form aggregates. These are all natural aggregates and are specified to conform to Eurocode BS EN 12620. It's possible to obtain recycled aggregates and recycled concrete aggregates for use in concrete, which should conform to BS 85002, and future lightweight aggregate is sometimes required and may be natural, but sometimes it's man-made. Aggregates make up 59-75% of concrete volume. Volume of cement occupies 25-45% of the past, and water makes up to 55-75%. It also contains air, which varies from 2-8% by volume. Very important, you must understand the strength of concrete is dependent on the strength of aggregate particles and the strength of hardened past. A wide variety of materials is available as aggregates for the making of concrete. For example, gravels, crushed stone, brick, furnace slag, and lightweight substances such as formed slag, expanded clay, and vermiculite. In making concrete, aggregates must be classified so that the smaller parts of the fine aggregate fill the voids created by the coarse aggregate. The cement past fills the voids in the fine aggregate, thus forming a solid mix. Aggregate is usually specified by the maximum size of aggregate included. Most structural concrete is formed using 20 mm aggregate, which means the maximum stone size in the mix should rarely exceed 20 mm. If there are large pours of concrete, large maximum aggregate sites are sometimes used. Structural concrete usually includes a mixture of sand and gravel, which are only combined at the mixer. Coarse aggregate size are not permitted to be below 4 mm, and the maximum sand size is set at 4 mm. The reason for using two different aggregate types is that if the aggregates were combined at source and then transported to site on a lorry, say, much of the sand would filter through the gravel voids to the bottom of the pile, so concrete made using the top of a pile would have different aggregate than concrete made using aggregate recovered from the bottom of a pile. The cement paste fills the voids in the fine aggregate, thus forming a solid mix. Aggregates should be clean and able to bond the cement paste. This is a gravel, furnace slag, formed slag, and expanded clay. If materials such as clay are stuck to the aggregate surface, cement paste will not bond to the stone and the strength of the mix will be compromised. Aggregates should not have excessive dust coating, which can reduce the bond between cement and stones and increase water demand. Other undesirable ingredients include pyrite, coal, and sulfate. If pyrite is in aggregate, it can compose and this result in staining of the concrete surface. Coal and lignite may swell during the life of the structure and they sometimes decompose. This can leave voids in the concrete. Some aggregates are susceptible to alkali aggregate reaction. And these aggregates contain particular silicates which can react with the alkalis produced when cement hydrates. When it occurs because the reaction is expensive, the concrete can spell and crack. Properties of aggregates. Compressive strength should be higher than concrete strength of 4120 megapascal. Voids represent the amount of air space between the aggregate particles Coarse aggregates contain 30–50% of voids and fine aggregates 35–40%. Moisture content represents the amount of water in aggregates, absorbed and surface moisture. Coarse aggregates contain very little absorbed water, while fine aggregates contain 3–5% of absorbed water and 4–5% surface moisture. When delivered to site, aggregates should be inspected before discharge. This said, it's important to ensure it's not contaminated with silt and clay. Rubbing and damp sample in the palms of the hand will indicate if impurities are in the mix. The field settling test will also reveal contamination, but both of these tests are only indication of the presence of contaminants, and if suspicions exist, detailed laboratory analysis should commence. With coarse aggregate, the material should be inspected visually and a knife used to scrape individual particles to ensure clay is not adhering to the aggregate. Coarse aggregate should be inspected to ensure it has not been placed in layer of the on the truck. All aggregates should be well mixed before loading. Layered loads should be discarded. Also, when delivered to site, aggregates should be tied onto a concrete apron laid to falls. Partition walls to separate different aggregates are essential, and a sensible means of discharging aggregate should be developed. If it's impossible to provide a concrete surface below the aggregate, the bottom 300 mm of aggregate should be discarded as contaminants from the ground can affect this zone. Aggregate should be stored in as large a pile as possible, as this helps to ensure an even distribution of moisture contents throughout the material. Leaving aggregate for 12 hours after any rain will usually result in a reasonably uniform moisture content except at the very bottom of the pile. With sand, so the time may need to be extended somewhat. In any case, the moisture content of aggregate should be regularly checked.